Hello, everyone. Welcome to another round of IRIS-HEP Fellow Talks. Today we have Shuo and Aman. Shuo and Aman were both mentored by Henry. Henry, do you want to say a few words to introduce Shuo's work?
Sure. So Shuo really doesn't need too much of an introduction for Hist, as he was the original author of most of the library last year. He had the Google Summer of Code project, so he wrote a good portion of the original Hist. This year, he was working on some NUMBA bindings for loose histogram, and whenever that got stuck, he also went back and worked on Hist as well. So he helped Aman quite a bit in Hist as well. So I think they'll even share a bit of the material because of that.
Hello, everyone. I'm Shuo, and in this summer I worked as an IRIS-HEP fellowship and worked on Hist program, a Hist project. Hist is a powerful analysis tool powered by both the histogram, and it extends both the histogram, including some important features. In this presentation, I'm going to use a dynamic Jupyter notebook to show some important features of Hist and how to histogram using NUMBA. Hist allows names for both the histogram axis. The names are unique identifier in a histogram, which are used to support some useful features such as fill and project. Especially Hist design named Hist to provide named shortcuts for the histogram that contain named Hist. With named Hist, all your operations on histograms should be subject to names, should subject to the names of axes. Here's an example. First, let's create 3 axes and create a histogram. So you can see the name of axis and labels. Then we can fill it either by the order of the axis or by its names. Note that you cannot directly operate on the name of axis, but you can try to modify it with bulk names. For example, this won't work since you are gonna to change the names of an axis. But if you are trying to change the label, it works. And if you are trying to change the names of all axes in a histogram, it also works. Hist has customized wrappers when displaying Jupyter Notebook and support dark mode. First, we try to project 1D histograms and then a 2D histogram. And the 3D histograms wrappers is shown as below. Besides the fancy wrapper, if you want to explicitly see the data, you can also try plot and show methods. Hist uniform histogram indexing plus extends both the histograms UHI and provide users with handy accessing shortcuts. For example, to access the centered elements of a 2D histogram, you can try the upper 2 method with both the histogram, but you can use any of the five method with Hist. UHI Plus also support ribbing for histograms with J shortcuts, the complex shortcuts. For example, in this example, you are trying to find the element of the .5 location, and you can even ribbing the histograms like below. Note that like you say, the histogram become wilder. Besides the standard construction of both histogram, Hist also provides pre-construct for HEP users. Normally, in both histogram, you are recommended to create a histogram by passing 3 axes or by passing some axes into it. But with .new identifier, you can create histograms like this one. And you can fill it either by the order of axis or by the names of the axis. Hist has Panda supports. You can read DIX or Panda data frames directly into Hist. For example, let's try a CSV file like this one. You can see the columns, the names of the columns. We can extract this data from this CSV file and create a histogram. We can show the histogram by a plotpy method. Hist also have some other shortcuts. For example, you can get the density of existing histograms and the profile of histogram. So one of the another major contribution in this summer is Hist numbification. An event loop is a programming construct that waits for and dispatches events or messages in a program. To speed up data analysis for hyperenergy physics, HISTOGRAM ecosystem is long for a fully number-filled event loop. The awkward and vector portions are mostly developed, but the histogramming step as one element missing from fully number-enabled event loop is still missing. We enable both histogram fill from inside number loop without stepping through Python. So our goal is to make this work. We want to create a number fill Hist function that use number decorator, and we want to fill the elements in the array. First, let's create an array and a histogram. To extend the number, we first need to create a Hist type and then teach number about our type inference additions. And we also need to teach number how to actually generate native representation for the new operations and how to run in the field. So let's time the Python version. As you can see, it takes 121 microseconds per loop, and we can then time the number version. You might be curious about why it becomes slower with numbification, but I want to say that is expected. The file is highly optimized and batched from both histogram. The number version won't be faster. It will be more nature and will save having to build an array one hit at a time and then failing. So that's the reason why it becomes slower. The only successful identifier of successfully running number function is it does not throw any warnings and errors. Then let's see the results. For the future, we plan to see if we can access compiled routines directly from number. We want to avoid duplicating field code, take advantages of both histogram performance, and we want to allow batch fields. We also want to allow access to access information inside number. So that is to say, we want to make h.access work inside number. Since currently number can't access anything on the histogram except the stuff we add it would be good now to add those things and get it through Access. So here's all of my work this summer, and thanks for your listening. Is there any questions?
Any questions for Shuo? Thank you, Shuo. Up next, we have Aman. Henry, do you want to say a few words about Aman's work?
Yes. So Aman is a other IRIS-HEP fellow. He's working directly on Hist. He's already become rather involved in a variety of different areas. He was a big part of SciPy 2021, and he ran the sprint for that, and has been pretty active in some of the other channels. So you probably noticed him before. His work was focused directly on improving Hist, and I think he'll be telling us a bit about some of the improvements that have been made.
So hello everyone. Today I'll be presenting Advancing the Hist Library project under IRIS-HEP Fellowship. My name is Aman Goel, and I was mentored by Henry Schreiner from Princeton University. A little about me. I'm an undergraduate student of engineering at the University of Delhi Cluster Innovation Center, and I'm majoring in information technology and mathematical innovations. So I was a fellow for summer 2021 under IRIS-HEP, and my GitHub and my email ID are my contact details. AmanGoel185. A little background about the HIST project, as Shuo talked about it previously. So HIST is a powerful histogramming tool for analysis based on Boost histogram. So we build on the Boost histogram, which is a library, which is Python, which basically binds Python from the C++ Boost library, and it performs efficient histogramming. What we do in Hist is we add on to those features and use the Boost histogram as a backend to the work. And it provides a lot of plotting options, tools, shortcuts, and new ideas. So the latest release of Hist is version 2.5.1. It was released 5 days ago, and it includes a variety of features and improvements that we talk about. So first and foremost, we'll talk about stacked histograms. So this was a feature that we've been planning for quite some time, and it was under development while we presented it at PyHead. So a histogram stack holds multiple 1D histograms in a stack, and the axes in those stacks are required to match. So what happens here is when the axes match, we are able to stack the values on one on top of the other, and it'll make more sense graphically. So the most common way is to create one with the categorical axes. Here we define a regular axis and then a categorical axis, and then when we populate it with data, we put them in a stack, and upon plotting, we get this kind of a plot in Hist. So this plot can also be obtained using these shortcuts. Hist.stack, and we pass all the three histograms within the shortcut. And we can also use other two shortcuts like from iter and from dict, which supports a dictionary. So basically we provide a dictionary and the stacking is done using that shortcut. So this plot is basically how a stack is, we basically have the outlines of the histogram. And if we want a more stacked representation in which the stacks are one on top of the other, we can use MPL-HEP. So we get the stacked style of plot via MPL-HEP, and but there is some but due to MPL-HEP, what happens is when we plot it directly, it reverses the order of stacking. So to prevent that order reversing, we slice it negatively, and when we do that, we obtain this similar stack from the previous plot that we had. So we just need to pass the argument stack is equal to true, and his type is fill. So when we pass this in the dot plot function, we get a similar plot. Now, what we can also do with stacks is we can print it to the console So we do that using histoprint. And so histoprint is a library that Hist earlier supported for all the histograms that we had. And now what we do is we also support it for stack by passing multiple histograms. And to do that, we simply just have to do dot show on the stack that we have, and it pretty prints on the console. So what this requires is the dependency on histoprint, and we can also pass different parameters that are there according to the histoprint library standards, and it will give us the corresponding graph on the console itself. Now, other things that were added to stacks are that we can also save names of the histograms that are present in the stack. And we do this when we access those names, it gives us a rep as Shuo talked about it. When we execute suppose we have a histogram that we're talking about and we execute the dot name on it, we get that histogram itself and the values as a rep, and we can access them. What we can also do is we can scale the stack itself. So when we scale the whole stack object, what we get is here we can see the values on the y-axis in the middle plot. They go from 0 to 16. But when we completely multiply it, when we scale it, it increases all the values along the y-axis. What we can also do is we can pick up a particular element of the stack and we can scale it in place. So here, what we do is we keep the bad the same and good is scaled up. So we can see how the scaling is done only for one and the other remains the same as the previous graph. And along with this, we can also perform various math operations on stacks. This happens via, we can multiply the stack by a scalar, or we can also add and subtract scalars to the stacks, and we can also add or subtract arrays to the stacks itself. Now, we have a very basic functioning of interpolation as of now, which depends on SciPy. So when we import SciPy, we're depending on the library, and we use the Hist library to basically pass it through SciPy and perform the interpolation on that. Here, what we see is first we define a histogram in Hist, and suppose this is our histogram. We then take the center of each of the bin values, and on those values, we plot against, we do a linear interpolation along the same. So interpolate dot interp 1d, this is present in SciPy, and we pass the center, the values, and when we pass kind is equal to linear, we get a similar plot upon plotting this. So here, as we can see, the linear interpolation takes place, and this is the plot that we'll obtain, and it will connect the centers since the values are interpolating along the same. And we can do a similar plot for cubic interpolation in which we change the keyword to cubic. So one drawback for the same is that SciPy is a heavy library, and what we have in place, an interpolator for Hist itself, we have a very basic interpolator in place which would use NumPy. It's a very basic class right now, and it has not been implemented in the development branch. But what it would do is instead of depending on SciPy completely, it would use NumPy to interpolate, and that way we can use the Hist functions itself. So we'll have shortcuts for that, and we can uh, interpolate over a value or an array-like value basically, and it would take the histogram and the array-like value while it performs the multiple interpolations. So another thing that we did was we improved the documentation and made it up to the standard with Boost histogram. So how structurally both the packages work are the Boost histogram provides the backend for Hist, and Hist builds upon those features. And when we perform the operation, it features it functions in a similar way. The documentation has been also been updated in a similar way. Earlier, what was there was Hist had a different kind of documentation from Boost histogram, but since we are performing similar operations and adding on to them, we use the same convention now, and we have made it up to date with Boost histogram. So the major difference for most of the functions there is that it depends on Hist rather than BH, that is Boost histogram. So instead of doing Hist dot, we do BH dot in a lot of places, and we build on that documentation. Now, talking about other features, as we talked about quick construct earlier, so with the help of quick construct, we can easily construct histograms in a single command. So now it also has directly passing of names and labels as arguments while defining the histogram. So suppose we take some data and then we define the histogram. So we pass the names and labels directly into the quick construct definition itself. So that is possible now in the latest update of Hist. We also have a hist.new alias for hist.hist.new. Earlier we had to go into the library. Now we can directly access it as a synonym, hist.new. We also dropped Python 3.6 support according to NEP 29. And now Hist uses Boost Histogram 1.2.x series, which includes all the features. And we also support Python 3.10. So that was added recently in Hist. And as we discussed earlier, we use SciPy for the interpolation itself. So packages like SciPy and Iminui, they are not actually needed. They are not provided as requirements unless they're actually needed. For example, again, if we perform an interpolation, we can import the SciPy library and then perform the operation. Then there is an improvement and clarity of treatment of confidence intervals in the interval submodule. And we use NumPy 1.21 for static typing, which basically updates all the static typing. So suppose it was earlier np.ndarray in a lot of places while defining the variables. Now it is np.typing.ndarray according to NumPy 1.21. And the tests are now supported without the plotting requirement. So they can be run without the requirements of plotting itself. And these are the features that we have in the latest release of the Hist library. So I would like to extend my sincere gratitude to Henry, who guided me throughout the project and helped me understand a lot of new concepts. And he answered every query and made sure that I understood everything. And he was kind enough to help me also present at HITOGRAMS. So that was a really great experience, and I'm really thankful for that. I would also like to thank Xiao for helping whenever I got stuck, and he helped me a lot through the code and through the stack itself. So we discussed a lot of things, and he got me up to speed with the project since he was one of the primary authors of the project. And I'm really grateful to the whole IRIS-HEP community for being warm, welcoming, and supportive throughout the fellowship. And apart from Hist itself, the community has been really supportive, be it through PyHep and SciPy, and also through Boost histogram contributions. It has been really great experience working with everyone. So thank you. That's my presentation for Hist.
Thank you, Aman. Any questions for Aman? No questions? Well, then that commences this round of fellow talks. Thank you to Shuo, thank you to Aman, and thank you, Henry, and thank you to all those who attended the talk. Bye.